All right, so today we're going to be talking about projectile motion. So it's going to build off of the kinematic equations we've already gone over, specifically the three that I have kind of laid out right here. So VF equals VI, final velocity equals initial velocity plus acceleration times time. We're also looking at final velocity squared equals initial velocity squared plus 2 times acceleration times the distance, length, however far the object's moving. Sometimes you're going to see the d as a delta x. That's how I typically like to do it. Today, though, we also have stuff moving in 2 directions, so you'll also see the d as delta y. That's just kind of the habit I've gotten into here. Both of those are just distances, just in different directions. And here we have distance, once again, either in the x or the y direction, is equal to the initial velocity plus the final velocity divided by 2. Really what this part's getting us is this is getting us the average velocity during the trip our object's taking. Doesn't matter what the object is. We don't need that there. All right, times time. Okay, so the average velocity times time gets us distance. Really, that one just looks an awful lot like velocity is equal to distance over time. We can solve for d by taking velocity times time. This is just the average velocity times time. All right, so actually, let's jump into this real quick. No pun intended. So let's say that I have a kind of a cliff here, and I have my ball here, and let's say that the cliff is a generous term for this. We're going to say that we are 5 meters off the ground. And let's say that we give this ball, let's say we're going to kick it straight out. Put like a right angle thing there. We're going to kick it straight out with a velocity of 8 meters per second. We're just launching something right off a cliff. We know intuitively that this ball is going to follow kind of a curved path. For all of these, we're going to assume air resistance is not a thing, just because that math is way hard. All right, so no air resistance here. We launch the ball at 8 meters per second, and we're also going to assume all of our problems take place on Earth. That's kind of important. All right, so for this, the two questions we want to know, actually the only question we want to know, how far away from the base of our cliff here did the ball land? So essentially, what's our change in position in the x direction? Okay, because if we look at this like it's a graph, we have the x direction going side to side, we have y direction going up and down. So if this is my change in distance in the x direction, that means, whoa, what just happened there? Make sure I'm still there. Technical difficulties are always fun. All right, that means the change in distance in the y direction is at 5 meters. All right, so let's start listing what we know. All right, so I know that the change in distance in the x direction is what we're looking for. Okay, so I'm going to leave that a question mark. I know that the change in distance in the y direction is 5 meters. I know I'm on Earth. So in Earth, I always know what acceleration due to gravity is. In this case, gravity is going to affect motion in the y direction, and that is negative 9.81 meters per second squared. I also know the starting velocity. So if this 8 meters per second is straight out in the x direction, that's going to be my velocity in the x direction. It's 8 meters per second. I'm going to take a moment to talk about that as well. That 8 meters per second, since we're ignoring air resistance, once it leaves the cliff, essentially, nothing's going to slow it down or speed it up in the x direction. So we should see no change in our velocity in the x direction. It should always be 8 meters per second, right? This is going to be different than what's going on in the y direction. Right off the bat, so I'm going to call right off the bat, I'm going to call that the initial velocity in the y direction. I know, multiple subscripts. Subscripts just give me information about the variable. So it's velocity, it's initial velocity, and it's in the y direction. Okay, that's all that the I and the y stand for there. essentially, if I was looking at the ball straight on, like I'm not looking at its path from the side, if I'm looking at it straight on, it's going to look like that ball is simply dropped off of the cliff, right? Ignoring depth perception, okay? It's going to look like it's just dropped straight down. If I'm looking at it, if I could like cut this and like rotate it so I'm looking straight on. And when I drop something, it starts off with a velocity of 0 meters per second. At that point, acceleration due to gravity starts speeding it up, right, at negative 9.1 meters per second squared. One of the things I'm going to need to find the distance in the x direction is, just bear with me here, is I'm going to need to know the velocity in the y direction. The reason why I need to know that is because I'm going to use that to find time. The only thing, what's going on in the x direction and what's going on in the y direction, the only thing they have in common is time. Because the amount of time it takes for that ball to drop, to move down in the y direction, is the same amount of time it's moving in the x direction. Like, that's what ties these two things together. Otherwise, my x velocity isn't going to affect my y velocity and vice versa. All right, so starting off with, if I'm looking at my y stuff, I got distance in the y direction, acceleration in the y direction, initial velocity in the y direction, and I want to know the final velocity in the y direction. Okay, so if I'm looking at those 4 variables, so if you notice now, once again, I'm looking at things in a specific direction, y. Essentially, we can look at these things in one direction as well. Like, we could have v Fy equals Viy plus acceleration in the y direction times either distance in the y direction or delta y. I like either one. I like delta y more. Don't know why. Just do. Same thing. Delta y, distance y, same thing for our intents and purposes here, okay? I can't have an equation that has y's and x's together when I do this, all right? And oddly enough, if I look, I've got delta y, so I've got the distance, I've got the acceleration, I know the initial velocity. Actually, the one that I copied was this one, actually. Let me go ahead and rewrite some of that. Plus, let's do square, 2ay. We'll just go dy. We'll do it this way for this, okay? This is the equation I'm going to use, because out of all of these equations, distance, acceleration, initial velocity, final velocity, that's what I'm looking for. This is the equation I want to use. All right, so let's start plugging in numbers. I'm looking for vf squared, so we're just going to leave that. Vfy squared. All right, 0, okay, so viy squared. 0 squared, 0, so I'm not even going to, like, write it down or anything. So now I have 2 times acceleration in the y direction, which is negative 9.81 meters per second squared, times distance in the y direction we said was 5 meters. All right, so VF y, and then to get rid of the square, we're just going to square root both sides. Okay, to save me a little bit of time here. All right, so let me get that math done real quick. Bring up the calculator, bring it over. So square root of 2 times, oh, hold on, 2 times, oh, one other thing. Our distance here, let me go back to there. I made one mistake. This distance is downward, because we're starting here, we're ending here. Our change of position in the y direction is negative, okay? So my negatives will cancel out there. All right, so 2 times negative 9.81. Okay, that's the negative one. Times 5 negative equals that. And now can I square root that? Okay, so I end up with, I don't know what's going on here now. All right, so So 98.1 is what I got when I do this math, and that makes sense. 2 times 5 is 10. Move that decimal over 1, okay? And it's going to be positive when the negatives cancel out. So I'm looking at the square root of 98.1. And that's, if I'm doing the math here, meters times meters is meters squared over second squared. 98.1, let's go square root, 9.9, okay? So equals 9.9. Now from square root, if I, were to square this number in order to get 98.1, I know that it can be positive or negative. So now I'm going to need to look here. So my VF is taking place right here in the y direction, so VFY. And that's downward, so I know that I need to go with the negative sign. And that's meters per second, all right? It's downward. It has to be negative 9.9. Okay, so we figured out final velocity in the y direction, negative 9.9 meters per second. All right, so we got one piece of the puzzle. With that part, now I can come find time. So I have VI, I have VF, I have distance, I also have acceleration. I can use either this equation here or this one here. They'll both give me the same answer. Okay, so it's just a matter of choice which one you want to use. And we can even prove it here quick. So let's start by looking at VF equals VI plus A times T. VF we found was negative 9.9 meters per second equals VI is still in the y direction is still 0, so I'm not even going to care about it. So I got negative 9.81 meters per second squared times t. Divide both sides by negative 9.81. I'm going to get an answer that's going to be about 1 point. All right, so 9.9 divided by 9.81. I know that my negatives are going to cancel. That's why I didn't include them there. You know what? I'm just going to even round that to 1 second. Okay, so 1 second. All right, that's how long it takes for this ball to drop, and that makes sense. 5 meters really isn't that high for something to fall. Now let's check it the other way using this one. So distance, so 5 meters equals VI, which is 0, plus VF, we said was negative 9.9. Oh, that should be a negative. That should be a negative, okay. Divided by 2 times time. So I've got 5 times 2, which is 10. Negative 10, since negative 5, divided by negative 9.9. So I've got 10 divided by 9.9. Round that off to 1, close enough. It's still 1 second. So like I said, you can use either that one or that one. You're going to get the same answer. You can use both of those to solve for time in this case, which is great. All right, so we know it's falling for 1 second. Let's even pop that in here. That's how long it's going to follow this path for. Our original question was, how far in the x direction is this thing going? So to address that part, we already kind of talked about the x velocity a little bit here. Once it's kicked off, that 8 meters per second in the x direction, without air resistance, nothing's going to slow it down. Nothing's going to speed it up either. So we can either look at it like VI and VF, our initial and our final values for velocity are that. And we could use this equation to solve for t, because my average velocity is just going to be 8 meters per second. Or one of the first equations we deal with is v equals distance over time. Well, now if we're just looking at velocity in the x direction and distance in the x direction, time doesn't have a direction to it. Thankfully, well, I really ruined that. So to solve for distance in this case, distance in the x direction is equal to velocity in the x direction times time. Well, that I can do pretty easily. The velocity we said was 8 meters per second. Time we just found out is 1 second, or about. So multiply these things together. Seconds cancel seconds. And our ball should go 8 meters away from the cliff, shelf, table, whatever it is we knocked it off of. It should move 8 meters away because it's only in the air for 1 second. All right, so because that wasn't long enough, I'm going to make another video dealing with what if we're shooting things upwards. So that's projectile motion horizontally off a cliff. All right, so stay tuned for the next one. Good luck.